Yes, guys. Sorry for the disturbance. So let's do like this now. So we went over this one, the whole example. We went over this for geometric distribution. I just would like, we went over this mean and variance too. I would like to go for one more example. Just you can read this, just a similar, this is just similar to the previous example. At a busy time, a telephone exchange is very near capacity. So callers have difficulty placing the calls. It may be of interest to know the number of atoms necessary in order to make a connection. So number of atoms we have to make to get the connection. Suppose that P equal to probability of getting the connection that is given to you, that is 0.05, with the probability that the connection during the busy time. We are interested in knowing the probability that 5 atoms are necessary for a successful call, right? That means 5 atoms are necessary to get the successful call, right? Successful call, that means once you are connected, that means your matter is over, right? That means your K equal to 1. Once you are connected, it's okay, but you have to do 5 attempts to connect with that particular guy or agency or what it may be. So K equal to 1, and that's why again, this is a part of your geometric distribution. So my X is equal to 5, right? Number of successive trials, and K equal to 1, probability is given to you 0.05. So that is P is 0.05 to the power 1, and Q is equal to 1 minus P is 0.95 to the power X minus 1, X minus K, that is equal to, naturally, that is equal to 5 minus 1, that is equal to 4, right? And if you use this one, just your calculator, and you are getting the probability. So that's how it works, right, guys? So that's what we mean by the geometric distribution. And please keep this thing in mind, that application of negative binomial distribution are similar in nature. I mean to say that, suppose atoms are costly in some sense and are of occurring in sequence. Okay, atoms are occurring in sequence, and they are costly also in some sense based on the real life situation. A high probability of needing a large number of atoms to experience a fixed number of success is not beneficial to the science or engineer, right? It may be possible that high probability of needing a large number of atoms to experience a fixed number of success is not beneficial to the scientist or the engineer. And there are lots of plenty of examples too. I would say that the oil driller defines a certain level of success from the subsequently drilling locations for the oil, right? So number of places they have to drill, and one success, they are going to get some success, but after number of attempts. So if only 6 attempts have been made at the point where the second success is experienced, the profit appears to dominate substantially the investment occurred by the drilling. So there are some examples, particular specific examples based on this one. Now we are going to see the another type of distribution, the last distribution, discrete probability distribution, that is called the Poisson distribution. Again, we are having the ready-made table on the back of the book. So you can make the printout of that one too. So this Poisson distribution, that is mainly, you can see here, Poisson distribution, again, that is for the random variable X. So my random variable X and the number of outcomes occurring during a given time interval or in a specific region. Now you can see over here, see number of outcomes they are occurring in a specific time period or specific region. Suppose you have one cardiogram, and cardiogram moves like this if your heart is working properly. But sometimes you know that what I mean, cardiogram, this just jumps like this, right? And again, so it's a very sudden fluctuation in a short period of time, just millisecond or something like that, very fluctuation. Whenever we have some success in specific time period like this, at that time we can use the Poisson distribution. I repeat, please keep this thing in mind, the number of outcomes occurring during a given time interval or a specific region. Specific region means in some locations like this, that is called the Poisson experiment. And the random variable and distribution associated with this one, that is called the Poisson distribution. That is the Poisson distribution. Now you can read this one. The X is the number of random variable, and the number of outcomes occurring during a given time interval on a specific region, or that is called the Poisson experiment. And the given time interval may be any length of time. As I told you, suppose it is 5 seconds, 10, 5 minutes, 3 minutes, something like that, length of time, such as the minutes, or it could be a day or week or month or year, depending on the real life situation, right? Some examples are given to us. A Poisson experiment, look at here, the Poisson experiment, telephone calls received per hour, right? Poisson experiments can generate observation for the random variable X, as I told you. Examples are the number of telephone calls received per hour by an office. Number of telephone calls are suppose 10 calls, 12 calls, 15 calls, sometimes 8 calls, depends, right? So number of telephone calls, but that is just in 1 hour. So we are measuring the number of successes during some certain time period. That means Poisson distribution. So when time period is included, means just think about the Poisson distribution. The number of days the school is closed, right, due to snow during the winter, right? Number of days the school is closed during the snow, due to snow during the winter time, peak winter time. Depends on different locations. Suppose you are in Minnesota or something like that, and where lots of snow is there at that time, the number of days of closing the school, that is more than the number of days of closing the school in Texas, like this. So it depends on different locations. The number of games postponed due to the rain during the basketball or baseball season. The specific region could be a line segment. Now we can talk about the region. As I told you, time or region, the specific region could be a line segment, some area, volume, something like that, some piece of materials too. In such instance, X might represent the number of fields mice per acre, number of field mice per acre, the number of bacteria in a given culture. See, just one culture and number of bacteria in a given culture, like this, or the number of typing errors on one page. So one page is your area, and how many errors are there on that page? This number of errors, that is your success in just in some certain time period, not time period, but the region. Region is a page. So on one page, you have number of errors, printing errors. So that is called the success rate. So that is just in one region, one area. So that's how it depends. So whenever you are talking about with the probability success rate with respect to some time period or with respect to some area, as I explained to you, that is nothing but the Poisson distribution. Always we think about the Poisson distribution, right? And X is a random variable, and the Poisson experiment is derived from the Poisson process, and that process that is called the, there are some properties of the Poisson process. First property, guys, please now keep in mind this thing. First property, the number of outcomes occurring in one time interval or specific region of space is independent of the number that occurs in any other disjoint time intervals of a region. See, disjoint time intervals in a region, that means, see, let me give you that example, that one page, that is the area, and number of errors, printing errors are occurring on one page. And then we can go for the second page. But this one page and second page, they are some completely separate, right? Whatever the errors occurring on one page, those errors would be completely different, could be similar, but completely different on the second page, right? In different lines, some different errors will be there on second page. Page 1 and page 2, there is nothing is common, because page 1 area is different, page 2 area is same but different, because both are separate elements, you can say. And we are looking for the number of errors on 2 separate pages, 1, 2, 3 separate pages, like this. So that's why they are disjoint set. You can say page 1 and page 2, nothing is common, because page 1 is over here, page 2 is over here, nothing is common, like this. Another way, suppose one person is going to the hospital for the cardiogram, is suffering from heart trouble, and suppose doctor measures the cardiogram for 5 minutes, right? And whatever the fluctuations is there on or some non-smoothing cardiogram for that particular guy would be different from the other person for same 5 minutes, right? Because person to person, they are different. There is nothing common between those two, because the chemical reaction in the body is completely different for both the person, all the persons, and that's why nothing is common. And that's why the small changes are there in the cardiogram for each of the persons. So this way, there is nothing common. So they are disjoint sets, 1 set, 2 sets, nothing is common. A intersection B equal to 0. That's what we mean by disjoint. So number of outcomes occurring in one time interval or specific region of space is independent of the number that occur in any other disjoint time interval of the region. And this sense, we say that Poisson process has no memory, right? Nothing is common. If some A intersection B equal to something, that means it has some memory. But if they are disjoint set does not have any, disjoint sets does not have any memory. So please keep this thing in mind. The probability that the single outcome will occur during a very long time interval of Now, or in a small region is proportional to a length of the time interval, or the size of the region does not depend on the number of outcome occurring outside this time interval or the region. Suppose you are measuring the cardiogram for a person for 5 minutes, and then after, suppose you stop. But it could be possible, suppose cardiogram is not smooth after 5-7 minutes, but they are out of the interval. That's why we don't count it. So that means you have to first fix your time interval or the region. And once you fix the region, whatever the things, whatever successes you are getting within the time period or within region, we are measuring only that part, not outside the region. I repeat, a probability that a single outcome will occur during a very short time interval or in a small region is proportional to the number of time intervals of the size or the size of the region, and does not depend on number of outcomes occurring outside the time interval of the region. If outside some fluctuations are there, we don't count. Third one, the probability that more than one outcome will occur in such a short time interval or fall in such a small region is negligible, right? Probability that more than one outcome will occur in such a small time interval or fall in such a small region, that is always negligible. And number x of outcomes occurring during the Poisson experiment is called the Poisson random variable. Number x is always the random variable. So random variable associated with this one, there is a Poisson random variable, and the distribution associated with this one, or probability distribution associated with this one, that is called the Poisson probability distribution, that is given by Poisson probability distribution. The mean of the Poisson probability distribution, that is given by nu equal to lambda t, where t is time, specific time period. Please keep this thing in mind. This is very important. The mean is given by nu is equal to lambda t. Why now t? First time we have introduced t. So t is nothing but the specific time or distance or area or volume, whatever it may be. That is my t. So please, this is a very important line, this one. So t is nothing but the time, distance, area or volume. And since the probability depends on this lambda, this one lambda, the rate of occurrence of outcomes. This lambda is the rate of occurrence of outcomes. So we shall denote them by px lambda t, and the Poisson distribution definition is given in the form of px lambda t is equal to e exponential function e to the power negative lambda t, because it repeatedly it increases or decreases. As I told you, cardiogram with a short time period, time interval, it just increases like this and goes smooth like this. And that's why it's a repeat function. That's why exponential function is being introduced. And lambda t, that is nothing but my mean to the power x and x factorial. Well, lambda is nothing, as I told you, that is in the average number of outcomes per unit time. Average number of outcomes per unit time, right? That is my lambda. So, and again, as I told you, that ready-made table is there. Table A2 contains the Poisson probability and probability of R lambda t. What is my R? If you take the summation of this type of things, summation over x could be 0, 1, 2 like this, 0, 1, 2, 3. Suppose you are measuring x equal to 0 to 5. So x is equal to 0 to 5, that is 5 is my R. Lambda t, that is equal to summation of, if you take the summation over the index x, that is denoted by capital P R lambda t. I will let you know how to use this one. If you have a book, you can open the book and keep the book in front of you, or you can open the book on your screen if it is possible, and try to open the table so that you will come to know this thing very easily. Good. Let's go for this example. Again, I'm going to use the whiteboard once we read the example, and then after we will be moving to some specific examples of the exercise. Already the assignment is there on Canvas, so please try to go through the practice test assignments, solve the examples and all these things. Don't keep things pending. During a laboratory experiment, the average number of radioactive particles passing through a counter is 1 millisecond is 4. So 4 particles, they are passing through a counter, and counter in 1 millisecond, in just 1 millisecond, right? That is a radioactive particle. So radioactive particle passing through a counter in 1 millisecond, just 1 millisecond, that is your t time. And lambda is equal to 4. So t and lambda is equal to 4. What is the probability that 6 particles enter the counter in a given millisecond, right? Now, average is 4. But what is the probability? Average is 4. Average. Look at over here. Lambda is the average number of outcomes. Average number of outcomes. But we are looking for some probability based on this average. So I'm going to write like this. Suppose my x is equal to 6, because what's the probability that 6 particles? So number of successes, 6 particles, that is x. Number of successes, small x, that is equal to 6. And my lambda t is equal to just 1 millisecond. Unit is millisecond. So t equal to 1. T equal to 1, lambda equal to 4. 4 times 1 equal to 4. So lambda t equal to 4 times 1. It is better to write 4 times 1. 4 times 1, and that's why we have. So let me share my screen and I will let you know how to use the book. So please, guys, let me share my whiteboard. Example number 5.58. Example number 5.58, and it says that, sorry, 5.17, right? During the laboratory experiment, 5.17. Example 5.17, and my x is equal to 6, my lambda is equal to 4, t is equal to 1. This implies that lambda t that is equal to 4 times 1, and that is equal to 4. And my definition says that small p, 6 and 4. This is my x and this is my lambda t, and that is equal to x and lambda t, right? And that is equal to, what is the definition? E to the power negative of lambda t, and lambda t to the power x divided by x factorial, right, guys? So that is equal to e to the power negative of what? 4. And then 4 to the power x is equal to 6 divided by 6 factorial, right, guys? How can you measure this one? Look at over here, e to the power negative 4, 4 to the power 6, and 6 factorial. You can directly go for this one, or suppose you want to use that formula that p, capital P r lambda t, that is equal to summation of small p, and here it is x and lambda t, and here it is x is equal to 0 to r. X is equal to 0 to r. If you want to use this one, in that case, you can write that is equal to summation of p and then x and 4 minus summation x runs from, because we are looking for 6. We are looking for x is equal to 0 to 6 and x is equal to 0 to 5. X is equal to 0 to 5. So 0 to 6 means here to here, 0, 1, 2, 3, 4, 5, and 6. So 0 to 6, that is here to here. 0 to 5, that means here to here. 1 to 5, that means we are getting 1. And that's what we are interested in. So px4, and here it is px and px4 and px4, and x runs from 0 to 6 and x runs from 0 to 5. That is equal to, if you now look at the page number, what is the page number? I would say page number, say, 734 of the book. Just wait, guys. 734, page number 734, and that is x is equal to, yeah, I will open the book, open that one for you. Just wait. 730. Okay, let me again share my book. This part is hard. See, 734, right? Okay, guys, look at here. Can you see my screen, guys? Okay, good. This is the page Poisson distribution. Look at here, Poisson distribution. In my example, that was r is equal to 6. So first of all, I need to see r equal to 6. 1, 2, 3, 4, 5, 6. R equal to 6. But simultaneously, I have to take care of my nu equal to lambda t. My lambda t was 4. Do you find any 4 here? No. That means I have to go on the back page. So if you go back side, r equal to 6, and here I can find 4, r equal to 6. And if you go over here for 4, that is 0.8893. 0.8893. So that is my first summation. Then second one was R equal to 5 and lambda t equal to 4. So 0.8893 and then now R equal to 5. Look at my cursor, R equal to 5 and here it is 4. So 0.7851. So 0.7893 minus 0.7851, that will give you the answer 0.1042. So what is the probability that the 6 particles enter the counter is a given millisecond, in a given millisecond. So that is a probability, this minus this part minus this part. So that's how you can solve the example. So here now we are using the table. You can see over here that table starts with 0.1. So page number 732, depending on whatever the R and lambda t means, new value is given. This new is lambda t, always keep in mind lambda times t, mean value. So what page you have to use, that you have to decide based on the example. So page number 1, 2, and 3, these three pages, they are based on the distribution. Next one, this is the normal continuous distribution we are going to see in the next chapter. But so let me again go back to my example, and that was page number 162. Let me go back to page number okay. Let me go back a little bit over here. So I am on my page almost. So that's what is given to us. Look at here, guys. That's what is given to us. So I told you 0.8893 and 0.7851, and that is equal to this one. Same way we have another example. Plenty of examples are there. You can go for these examples. If you read this example, 10 is the average number of oil tankers arriving each day at a certain port. The facilities at the port can handle at the most 15 tankers per day, right? 15 tankers per day, there is the possibility on the port. What is the, that is the actually the capacity or facility, you can say. What is the probability that on a given day, tankers have no turn away? No turn away, that means if you have more than 15, that means it would be turned away. But less than 15, port has a capacity to keep those 15 tankers. Means I can start like this, probability of x is greater than 15, but x greater than 15 is nothing but 1 minus x is less than or equal to 15, because 15 tankers is the, can be occupied on the port. So that's why equality sign will be over here. So 1 minus, now x is equal to 0 to 15 and px and 10, right? Because lambda t is equal to, just look at over here, what is my lambda t? The average number of oil tankers arriving each day on the port. The facility at the port can handle at the most 15. What is the probability that on a given day there have tankers have to be turned away, right? So lambda t, that is equal to, lambda is equal to, what is my lambda here, guys? Just make sure my lambda is equal to, 10 is, I'm sorry, it's given. 10 is the average number of oil tankers arriving. So lambda is equal to average number. Lambda is always the average number. And 1 day, your per day means your time t equal to 1 day. So lambda t equal to 10 multiplied by 1 is 10. So that is why lambda t is equal to 10 over here. Lambda t is equal to 10. So now again, you can use the table. My R value is 15. R value is 15, new value, that is lambda t is equal to 10. So just look at the table and matching the value in 15 and 10, whatever the value you are getting, the common value in the table, that is this one. That is this one. And that is equal to, again, running out of time, what's going on? But I think we are almost done, right? 10:41, okay, that's fine. And we have 10 minutes. So this is the probability. And then after we can go for the natural approximation of binomial distribution by the Poisson distribution. The approximation of binomial distribution by the Poisson distribution. Look at over here. And it should be evident. Look at here, guys. It is very important just for the knowledge. Of course, we are going to use only theorem 5.5. It should be an evident from the 3 principles of the Poisson process that the Poisson distribution is related to a binomial distribution. Although the Poisson usually finds the application in space and time problems. It has lots of application in space and time, in the space. Okay, and missile problem, robotics problem, aircraft problem, lots of applications are there, statistical applications. Okay, it can be viewed as a limiting form. It can be viewed as a limiting form of the binomial distribution. See, because now we have some limitation of time, and that's why the you can say synchronizing of the binomial distribution in terms of time or region, that is called the Poisson distribution. In case of the binomial distribution, n is quite large and p is small, and conditions begin to simulate the continuous space or the time implication of the Poisson distribution. That's the major difference. The independence among the Bernoulli trial is the binomial case is consistent with the principle of Poisson process. Okay, that's fine. So let X be a binomial random variable and probability distribution d, X, and P when n tends to infinity, P tends to 0. Means number of trials goes to infinity and probability tends to 0, extremely small, then NP tends to nu, remains that binomial distribution that is approximated by the binomial distribution is approximating the Poisson distribution. Look at over here. So whenever we have this type of, if n is large and p is close to 0, n is large and p probability is close to 0, the Poisson distribution can be used with nu equal to np, nu equal to n times p. They approximate by n to approximate the binomial distribution, right? So Poisson distribution is used to approximate the binomial distribution whenever your n is large enough and p is close to 0. The Poisson distribution can be used with nu equal to np to approximate the binomial distribution. If p is close to 1, sometimes it may be possible that p is not close to 0, but p is close to 1, right? Probability is not other than this side, but it is other side, very high probability. So we can still use the Poisson distribution. Even though in that case also we can use the Poisson distribution to approximate the binomial probabilities by interchanging what we have defined to be success and the failure rate. So just interchange of for success and failure rate. Of course, we are not interested in that part. We will be dealing mainly because once you understand this part, other part is not that difficult. So n is large enough, p is small enough. Just keep this thing in mind. And then after we have another example, and next time we will be solving because just 1 minute is left out. One minute is left out, so it's not possible for us to go over the exercise problems. We will be solving the exercise problems next time. But right now, I would say that a certain industrial facility accidents occur infrequently. It is known that the probability of an accident on any given day is 0.005. Now, probability is given to you 0.005, and accidents are independent of each other. What is the probability that in a given period of 400 days? See, now you are given t equal to 400, t equal to 400 days. What is the probability that what is the probability that in a given period of 400 days, there will be an accident on one day? There will be an accident on one day. So again, you can write your n is equal to this n equal to total periods, total samplings. So 400 days, so n equal to 400. And my probability p is given to us that is equal to 0.005, right? 0.005, that is the probability. So I can write that is equal to e to the power np. What is my np? Nu is equal to np and np equal to lambda t. And p equal to lambda t. Let me, I think, use my whiteboard. Just p value is given to us, n is equal to given to us, 1 day means t equal to given to us. 1 day is given to us. What is the probability that there are at the most 3 days with an accident, right? 3 days with an accident. So we are going to solve these problems, these two problems, and that problems are like this. Okay, so let me solve this one. And we'll stop. So it says that let X be a random variable. This is the example number 5.19. Sorry, 5.19. And X is the random variable with N is equal to 400 and P is equal to 0.005, sorry, 0.005. And my NP is equal to 400 multiplied by this one, that is equal to 400, and P is equal to 0.005. And that will give you 2. So my value NP equal to nu. This is my N nu, or that is equal to NP. So probability of lambda or X lambda t that is equal to probability of 1 and 2, and that is equal to the power negative lambda t and lambda t to the power x divided by x factorial, and that is equal to the power negative 2 and 2 to the power 1 divided by 1 factorial, and that is equal to, just use your calculator, you are getting the answer. That is your first part. And the last part, your here probability of x is equal to 1. And now I have probability of x less than or equal to 3, that is equal to summation x is equal to 0 to 3 and x is equal to 0 to 3 and e to the power negative of lambda t and lambda t to the power x divided by x factorial, and x runs from 0 to 3, that is equal to x is equal to 0 to 3, and here we are getting e to the power negative 2 and 2 to the power x divided by x factorial, and just use your x equal to 0, 1, 2, and 3, you're going to get the answer. So that's how, let me stop over here, guys. So that's how we can so that's how we can solve the examples based on Poisson distribution. Next time we'll be solving the exercise problems, and immediately we will jump over to the next chapter, that is a continuous probability distribution. Thank you guys for a couple more minutes. Thank you.
Thank you, sir.
Have a great day.
You too. Thank you.